Here are the notes for section 7.4, exponential growth and decay. So we're going to start with separable differential equations. So a differential equation of the form dy dx or y prime, f of y times g of x is called separable. We separate the variables, write in the form 1 over f of y dy equals g of x d of x. So essentially you're getting all your x terms to one side, all your y terms to the other. So solve for y if dy dx. So let's rewrite it a little bit to make it a little bit easier to see. So I want to make this x squared y squared because I need to be able to get my x and y apart. So what's going to happen is dx is going to come over here, and the y term is going to come across. So it's going to be, if you notice here, you have 1 over f of y, so it's going to be 1 over y squared dy equals x squared dx. So we've got our variables separated. So to have these dy terms, I need to take the antiderivative of both sides. So over here, this one's relatively straightforward. That's x cubed, and we'll put our plus c over here. Now this one, remember, this is actually y to the negative 2. So if I count up the exponent, I get negative 1, and then reciprocal out front. Make it look like this. So let's see here. We can find the value for c because I know the value that x and y go through. So if y is 1 and x is 1, so this becomes 1 times 1 to the negative 1 equals 1/3 times 1 cubed plus c. So this is negative 1 equals 1/3 plus c. So c is negative 4/3. So now I come back up here. So negative y to the negative 1 equals 1/3 x cubed minus 4/3. So I'd have this equation. So let's see here. What can I do? Well, I've got a common denominator, so I should combine these guys. So that's x cubed minus 4 over 3. 1/3 x cubed is the same thing as x cubed over 3. So we've got the negative, so I can multiply or divide by a negative 1, which would actually just reverse the order of the terms in the numerator. And lastly, so this is 1 over y. So to get rid of that negative first power, I can raise everything to the negative 1, which effectively just takes the reciprocal. So this function would have that derivative. And if we really wanted to check, we could actually work it out, but that's what the equation for y is. All right, law of exponential change. So it says the differential equation describes exponential growth as dy dt equals ky. So we're talking about in terms of time, where k is the exponential growth factor if it's a positive number, or exponential decay factor if it's a negative number. So here's our formula for the law of exponential change. So if y changes at a rate proportional to the amount present, so meaning the derivative is some multiple of k, and if y equals y0 when t is 0, so y0 is our starting amount, this equation is actually the exponential form. Growth if k is more than 0, decay if k is less than 0. And then this version here is what the continuously compounded interest formula is. So example 2, suppose you deposit $800 in an account that pays 6.3% annual interest. How much will you have 8 years if the interest is compounded continuously? So the amount of money I have after 8 years is equal to my starting amount, so P. E, the interest rate is 0.063, and my time is 8 years. So after 8 years, and those are all numbers, so that can all just go to my calculator. So 800 e to the 0.063 times 8. So after 8 years, I have about a little bit more than $1,300. Now compounded quarterly, and we've got a little bit different thing here. Bring this up here. The formula for compounded interest looks like this. So where P is the principal, R is your interest rate, N is the number of times that is calculated per year, and T is time in years. So once again, so A of 8, so 8 years later, I'm putting $800 in, 1 plus 0.063 divided by 4 times per year if it's quarterly, and my exponent's going to be 4 times 8, or 32. So once again, all these numbers, so I can just plug numbers straight in. So 800 parentheses 1 plus 0.063 divided by 4 raised to the 32nd power. So 1319.07. So I end up with slightly more money if I compound continuously, which makes sense because this is calculating interest essentially every instant of every day. This is, I get interest added into my account 4 times a year. So say, maybe every 3 months. So I start in January 1, and then in March 1, interest is calculated. And then in, what would be 6 months later, April, May, June, interest is calculated again, but it's calculated on the account balance, which already has some interest in it, so on and so forth. Okay, radioactivity is a variation or type of exponential change. So the half-life of a radioactive substance is the time required for half the nuclei to sample to decay. So for example, carbon-14 is about 5,700 years. So if you start with 10 grams, 5,700 years later, you have 5. After another 5,700 years, so 11,400 years total, you're now down to 2.5. After another 5,700 years, you're now down to half of 2.5, so 1.5. So you keep taking halves. So it's not, you don't decrease by the same amount every time, you decrease by the same percent every time. All right, so found the half-life of radioactive substance with the decay equation y equals y0 e to the negative kt, and show the half-life depends only on k. All right, so if I need to find the half-life, it doesn't actually matter. I can choose any values I want for y0 and y. So I'm going to choose numbers that are easy to take in half. So we're going to say we start with, let's say, 10 grams of whatever. So if I want to find the half-life, so y is going to be 5, half of it. So then I have e to the negative kt. So let's see here. So we would divide by that. So that's 1/2 equals e to the negative kt. So to get rid of the e, I need to take the natural log of both sides. So when I do that, the exponent comes out front. So I have ln, which is 1, so it goes away. Now I'm going to actually do a trick here. This is the natural log of 2 to the negative 1. And the reason I want to do that is that I can make this then the negative natural log of 2 equals negative kt. So divide the negative k across, I get ln 2 over k is equal to t. So the only thing that shows up in the half-life, the amount of time it takes me to get halfway there, is k. And that formula is written down here. So the half-life is given by the natural log of 2 divided by k. So you can work this actually either way. If you know the half-life, you can use that to find the value of k. If you know the value of k, you can use that to find the half-life. Right, so example 4, at the beginning of the summer, population, that should be of a hive of bald-faced hornets, which are actually wasps, is growing at a rate proportional to population. From a population, so that's our y0 is 10. The number of hornets grows to 50, so that's our y value, and t is 30 days. The population continues to follow the same model. How many days after May 1 will the population reach 100? So I need to find my value for k. So this is growth. So let's see here. How do I want to do this? Do I want to use an E? Why don't we use an E? It'll make it easier. Let's see here. Actually, there's a faster way. So we're growing by 5. So let's say, so 50. Actually, we don't need to do that because we know it's going to go up by 50. Okay, sorry, we can do this faster. So y equals 10 times 5. And our time, we're going to use count in units of 30 days because that's how long it takes to do a multiple of 5. So every 30 days, it multiplies by 5. So this is our formula. We know when it was going to reach 100, so I can put 100 equals 10 times. So it could look like this. Let's see here. So divide both sides by 10. Gives me this. So then our natural log step, so natural log of 10 equals t over 30 times the natural log of 5. So I need to divide by the natural log of 5 and multiply by 30 to get out from underneath. So t is going to equal 30 times ln 10 over ln 5. So let's see here. 30 times ln 10 divided by ln 5. It's going to take about 42.9 or about 43 days to get there. Now, the one thing to be careful of is this formula is 5 is our multiplier. We go from 10 to 50, so that's why that's 5 there. But it takes 30 days, so the exponent is t divided by 30. Because every 30 days I get a multiplier of 5. So that can't just be t up there, because it's not every day multiplies by 5, it's every 30 days multiplies by 5. You can do that for half-life. You can put a 1/2 instead of using the E formula. You could do y1 or y0 times 1/2. If something doubles in population, you could put a 2 there. Okay, so scientists who use carbon-14 use 5,700 years for its half-life. I just talked about this. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. So we're going to start with 100%. It's a half-life problem, so half of it, and it's going to be t over 5,700, because every 5,700 years we lose half of it. So if 90% have decayed, I have 10% have decayed, I have 90% now. So this is the equation that I'm looking at. So divide the 100 across. So you could have actually started here if you wanted to be honest. Start with 1, 90% is 0.9. So natural log on both sides. So bring the exponent out front. We're going to change the decimals because why not? ln 0.5. So we're going to have to divide that across and multiply by 5,700. So t equals 5,700 times ln 0.9 over ln 0.5. And then that can all just go in my calculator. So 5,700 times ln 0.9 divided by ln 0.5. So t is 866.4, and our t unit is in years. It's going to take about 866 years. So that's how old the thing is. All right, so this formula here is Newton's laws of cooling. So T is the temperature of the object, S is the temperature of the surroundings, T0 is the temperature the object starts at, K is some constant depending on the object, we'll probably have to find it, and T is the time. So here it says a hard-boiled egg at 98 degrees Celsius is put in a pan under running water 18 degrees Celsius to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take to reach 20 degrees? So let's see what it gives us. So T0, the egg starts at 98 degrees. TS is what it's sitting in, 18 degree water. After 5 minutes, so that's T, the egg's temperature, so is 38 degrees. So that's all the information that I know. So I don't have K, so I have to find K first, but I can fill all my numbers in. So 38 minus 18 equals T0 is 98 minus 18, e to the negative 5K, because T is 5. So this is 20 equals 80, e to the negative 5K, divided across, so that's 1/4, equals e to the negative 5K. Take the natural log, we're going to switch to decimals, ln 0.25 equals negative 5K, whoops, ln e, which goes away. So K is equal to the natural log of 0.25 over 5, which is actually negative natural log of 4 over 5, because 0.25 is 1/4. So I can take the reciprocal if I put a negative out front. So how much longer will it take to reach 20? So now that's my new T's final temperature here. So start the problem over essentially. So 20 minus 18 equals 98 minus 18 e to the negative ln 4 over 5 times t. So this is 2 equals 80 e to the negative ln 4 over 5 times t. So divide it across, so 2 over 80 is 1/40th equals e negative ln 4 over 5 times t. Natural log both sides, so ln of 1/40th equals negative ln 4 over 5 t times ln e, so that goes away. So I'm going to have the natural log of 1/40th divided by the negative natural log of 4 over 5. So this is what I'm looking at. Okay. I think I lost this term somewhere. Let me go back and look real quick. So this, which means that should be negative, which means that should be positive. So it comes, yeah, never mind. It comes out to be negative there at the end. So I missed some signs earlier, but it comes out right because the negative sign goes back in. Okay, so let's see here. The natural log of 1/40th divided by the negative natural log of 4 divided by 5. So I get t equals 13.3 minutes. Okay, so now this is cooling from 98 degrees. So, but the question says how much longer will it take to reach 20? So it took 5 minutes to get down to 38. So if I subtract 5, it's going to take 8.3 more minutes to get from all the way down from 38 to 20. So it dropped 60 degrees in the first 5 minutes, and it's going to take 8 more minutes to drop the last 18 degrees. And that brings us to the end of the section.